Alright guys, this target problem is very similar to something you would have to do on my task next week. So I want to make sure that you feel comfortable with it. Making sure that you know all the little ins and outs, the little things that the calculator can do to make it easier. I'm going to go through those steps with you up here so you can make notes accordingly. First of all, hopefully you were finding the area that's in this shaded region in between these two curves. Next, in order to find that area, you are going to need to know what these intersection points are here. This area, we are going to be looking at it in terms of x, because I can see this very clearly as an upper function minus a lower function. So on those intersections, I am going to want the x values of those intersections. Now I'm going to make a note over here that I'm finding what a is equal to and b is equal to. A is going to be the x value of the first intersection over here. B is the intersection of the second, the x value there. Now, I recommend that when you're taking the AP exam or my test that you make notations just like this. The reader will see, just like I would see your entire test paper, they'll see the entire work section for that problem, and they'll grade all of it. They will look specifically to see that you have these intersection values correct. So I'm going to put all of the decimals for it there, but I'm going to get the calculator to store it so that I really don't have to keep typing those in. I'll show you that step. All right, so first of all, ny equals, I have those functions already in there. So I'm going to hit graph, and that is pretty much the same screenshot that you saw. So I'm going to get it to find those intersections. Now, some of you, not very many in this class, but I have noticed that a lot of students are still just hitting trace, and they're following one of the functions, and they're getting close to wherever the intersection appears to be, and they're writing down what that x value is. That will not give you the exact intersection. So you would not get the point for knowing where those intersections are on a test. To find the exact intersection, you need to do second first and then trace, and then choose option 5 where it finds the exact intersection. Now it still hasn't found it. You got to get it to go through the steps. It's asking you, is that the first curve, the x? You say yes by hitting enter. Second curve is 6 minus 0.5 x squared. Hit enter again. And when it says guess, that means you have to hit enter again when you are close to the intersection that you want the calculator to find. I want it to find this one, so I'm going to hit enter right there. And sure enough, that gives me negative 3.454971. So I'm going to write that down over here. Negative 3.454. Was it 971? Yes. 971. All right, now, before I go anywhere and do anything else or find the other intersection, I'm going to get the calculator to store that value so that I don't have to write it anymore. The way that I do that, I'm going to do second and mode. When you do that, you go back to the regular screen where we're going to do calculations. I'm going to hit clear, and I'm going to type X. When I hit X and enter, notice the same value that I just wrote down. The calculator remembered the last x value that I found. So now I can store that value. Hit STO, which is over the on key, and I'm going to store that as alpha A. Hit enter. Bless you. Now I'm going to go back to the graph, and I'm going to find the second intersection point. So second trace, option 5. 1, 2. Now I'm going to get close to the other intersection. It's asking guess, but if I hit enter too soon, it's going to find the other intersection again. So I'm going to get close to the other intersection. Enter. And then it has it 1.563. And then 8514. So I've got those in there. Yes.
How many decimal places do you want? Just whatever they're calculated for?
I would do all of them that the calculator does. You have to have more than 3 though, because this is an intermediate answer. It's not the final answer. All right, now from there, I'm ready to set up the integral. On the integral, those intersections are going to be the bounds. The lower bound is A, so I'm going to put A. Upper bound is B, so I'm going to put B right there. AP Reader is fine with that. Next, I need the function, the upper function minus the lower function. The upper function is which one of the functions? G of x. So I'm going to put G of x here. Now, let's say on my test, I had put y equals on both of those. Well, I stored this first one, put it in my calculator as y1, and the second one I put it in as y2. You might want to make a note to yourself that you did that so that in here you can even put y2, as long as you got it noted on your paper as to what it was that was stored as y2. All right, and then minus the lower function in this case is going to be f of x. And then we put dx. Guys, that right there gets you another point for having the setup. You don't have to go back and change anything. Put in all those numbers. So that's a nice feature. The last point that you would get for this is getting the correct answer. So again, on the calculator, I can get it to do the work for me. I don't know if I stored this answer. I don't think I did. Nope, so I'll do x equals, and I'll store that as alpha b real quick. All right, so now to do the integral, I'm going to go math 9. I want y2, so I'm going to use bars. Go right arrow over to y bars, number 1, and then I need y2, so that's number 2, minus, I need y1, so again, bars, right arrow, 1, and 1 again for y1, comma, now I need that in terms of x, comma, my lower bound is supposed to be alpha A, comma, upper bound is alpha B. What is that? Hit enter, and you should have gotten 17.856-ish. Y'all get it? Now you might want to start practicing with the calculator so that you can work that way. And the calculator is doing the heavy lifting rather than you.
Will we ever have this without a calculator?
If you did, these would be nice values that you could find easily by hand. Otherwise, you're going to have a calculator. Same thing, these functions that would be sitting here would be nice things to where you could easily take the antiderivative. Okay? All right, now, part B is not a question that you all know how to do yet. This is the target. This is what we're shooting to try to hit with today's lesson. So after I finish all of the class examples, you should be able to do part B here. Now I'm going to show you how it's different from part A, but again, we're just going to talk about the idea behind it. We're not actually going to work this one today. Now on this one, rather than asking you to find an area like part A did, notice part B, it says find the volume. You're finding the volume of a solid that has base area described in A, and cross sections that are cut perpendicular to the x-axis that are squares. Now, volume, that means it's a three-dimensional figure. You're looking at a two-dimensional representation, so you have to be creative. You have to think about this in 3 dimensions. It says that this is the base. I like to call these mathematician paperweights. You all have very little experience with what a paperweight is. Have any of you ever seen a paperweight? Okay, very good. Paperweight, if you don't know what a paperweight is, back in the 40s and 50s and 60s, before we had air conditioning, we had fans, we had windows, they needed to ventilate things. They'd open the windows when the wind blows or if the fan's blowing. If you're sitting in an office building that has lots of papers, what happens? Fly away. Okay, so they use paper weights. They put them down on top of the paper and it weights them down so they don't fly. So the paper weights really could have just been a rock. They could put a rock on top of it and that would work beautifully. However, that's not always what they did. They got, especially later, they wanted to make fancy paper weights. My mother had one that was, most of the fancier ones were flat on the bottom. Okay? My mother had one when you picked it up and looked at the bottom, it was a circle.
My dad had one, you picked it up and looked at his, and it was a triangle on the bottom. But they could have been any different shape. This mathematician's paperweight, when you pick it up and look at the bottom, you saw this shape that is this yellow region right here. So that's the bottom of the paperweight. Now my mother's, it was a nice little dome shape. So if I cut cross sections of that, cutting down toward the circle, perpendicular to the circle, but if I was cutting that way, what shape do you think those cross sections would have been? A complete circle? Half circle, like a semicircle. Can y'all imagine that? Because it was kind of a dome shape. Now my dad's, it was triangular on the bottom, but his, if you had done cross sections, you would have gotten triangles. Yes, there you go. So you're going that way. Can y'all kind of see it? All right, now this one, it says when you cut this one perpendicular to the x-axis, which means you would have come in here, a cross section would have gone through and cut the thing like this. In that red section, that is going to be coming out at me as a square. The cross sections are in the shape of a square. So the distance that I just drew here in red is coming up off the page, off this computer screen here, is a square. That means that over here, this is the base of a square. Will you agree this square that's coming up at me is not going to be as tall as the first one I drew? Okay? Same thing over here. If I get this one over here, it's not going to be as tall as the one that I drew there in the middle. Make sense? So this paperweight, that's what it looks like on the bottom, but if you were to look at it in its three-dimensional form, will you agree it's going to have kind of ridges on the top? It's going to be kind of flat on the sides, but it does have some shape to it. You know, kind of imagine it? All right, so we've got to find the volume of that. Now, when I first started doing these myself, when I was a student, and whenever I knew that I was going to have to teach it, I was very worried about teaching this because getting students to understand what this looks like is difficult. And you see what I've gone through and just trying to get you to visualize this one. The woman that I had for the workshop over the summer before was asking her about it, and she said, it doesn't matter if they know what the final product looks like. It would be nice if they did, but it's not necessary. All they're going to do is set up an integral, and that integral, they're going to base it on whatever shape the problem tells them. So when you look at this, in any problem that you get, if you can't imagine what the finished product looks like, the solid, don't worry about it. You're still just going to go for whatever cross-section shape it tells you. Okie doke? Now we'll come back to this problem, but we're not going to finish this one right now. That's the idea behind what we're going to be doing. We're going to look at an easier one first. But before we do that, these are the formulas that we're going to be using. Now, to help you understand where these formulas come from and why we use them when we're trying to find the volume with that known cross-section, when I find the volume of any particular figure, let's say it's a cylinder or a pyramid or a prism or what have you, will you agree with me that I need to know what the area of the base of the solid is?
Yes.
If it is a prism or a cylinder, what do you do once you know the area of the base? Multiply by its height. Okay? So if you know the base and the height, you're in good shape. All right, now let's imagine that we go over to Publix, go to the deli section, and they tell us that they want us to figure out the volume of one of these pieces of meat. Well, if it's a canned ham, I'm not going to have trouble finding the volume of it. How about you all? What shape is a canned ham? Cylinder. We can find the volume of that without an issue. However, if they give me a turkey breast, that's not going to be as much fun to find the volume of it. Will you agree?
Sure.
All right. What we're going to do is use the same idea as the cross sections. All right. If I knew what the area of the cross section was, if the cross section was a semicircle or the cross section was a circle, even though that turkey breast, whenever I slice it up, Each one of those slices could be a bigger semicircle or a smaller semicircle, bigger circle, larger, smaller circle. I still could find the volume of each one of the slices. Will you agree with that? All right. So in looking at this integral, that really is what we're talking about. We're going to find the area A at y or A at x. A at y or A at x is standing for the area of that cross-section shape, the area of the base of that slice, so to speak. What do you think the dy or the dx is standing for? In terms of the slice of the meat, what would the dy or the dx be? The thickness. Isn't that going to be the same thing as the height of that solid slice? All right, so this is area of the base times the height. The thickness is the same thing as the height. And when you do the integral from A to B, that means you're summing up all the slices. Each one of these is the volume of one slice, and then summing up the integral is going to give you the sum of all the slices. Make sense? All right, so let's look at an easier problem than the target problem that's still the same type thing. This is my example number 2. Says we got the base of the solid figure, base of this paperweight, is the region between the x-axis and the inverted parabola y equals 4 minus x squared. Weight. So that's what the bottom of the solid looks like. And then it says some very key information. It says that the cross sections are going to be cut perpendicular to the y-axis. All right, now if I'm cutting perpendicular to the y-axis, am I slicing this thing vertically or horizontally? Horizontally. So in other words, it's going to go through something like this. Does that make sense? Slicing coming straight down at it. Now the significance of that is that tells me that out here at the end, do I want a dx or a dy? Dy, very good. That means that this integral, both the function that I put here and the bounds, they're going to have to be in terms of y. I have to make sure that everything is in agreement. And here's another thing that I think is kind of cool. Will you agree that when we make the slices for these cross sections that we are cutting the y-axis?
Yes.
All right, wait for it. That's what this says too. You're cutting the y-axis. If you had gone vertically, you would be cutting the x-axis. But we're cutting the y-axis because we're going sideways.
Should make a rap about
Isn't
that.
that good? We like it. All right, now, from here, the bounds that I put right here, those are going to be the part of the y values that are the part of the y-axis that I'm actually cutting. So what is the lowest y value? 0, right down here. And the highest y value is 4, because notice that was y equals 4 minus x squared. So the highest value up here should have been a 4. Well, if you're stopping at the x-axis, the y value right there is 0 where you're shading. All right, next, from there, not only are the cross sections cut perpendicular to the y-axis, but it says those cross sections are supposed to be semicircles. That means that the formula that I've got to put on this line right here for my function is going to have to tell me how to find the area of a semicircle. Now imagine what a semicircle looks like. What is the formula for finding the area of that? Pi r squared is a whole circle divided by 2. So you could do 1/2 of pi r squared. Now if I'm grading your test, you've got 3 points. 3 out of 5 points right now. You would have gotten 1 point for having the correct bounds, another point for telling me that it was supposed to be dy, and another point for knowing the correct formula for that shape that it said the cross section was. Now from here, I'm not done because 1/2 and pi are numerals. I don't have to worry about those, but r is a variable, and it's a different variable from
from this y over here. The dy tells me that that r has got to get in terms of the variable y. So let's talk about how to make that happen. This cross section that I have right here, will you agree that the radius on the cross section would be right here? If I convert that back up here to the drawing on the parabola, hopefully you'll agree that the radius would go right in there. It would be from the y-axis over, and it would touch the parabola. When it touches the parabola, that means it touches an xy ordered pair. Does that make sense? Now, that point that it touches the parabola, it's an xy ordered pair. This distance that I just drew in for the radius, does that have to do with the x or the y value for that parabola? It has to do with the x. So that means that this radius is actually an x value. So update, I've still got the bound 0 to 4. I've still got 1/2 pi. But instead of the radius being squared, the radius I know is an x value that is squared. So far so good? Right, now I've got this in terms of a different variable, which luckily is in my equation, but it's not quite in terms of y. Remember the equation that we're working with, y is equal to 4 minus x squared. Before I can be finished, I need to get x squared in terms of y. What is x squared going to equal? 4 minus y would be 4 minus y. There you go. Move the x squared over and then move the y over. Okay? So that means right here, update again, we got from 0 to 4 of 1/2 pi. And then instead of x squared, we're going to put in 4 minus y and then dy. That is your complete setup. You can then put that in the calculator and it will spit out your final answer for you. Okay? All right, we got 6 minutes. I want to think that same problem, but then I want the cross section still cut perpendicular to the y-axis. I want them, instead of being semicircles, though, this time I want them to be squares. Think about that with me. Cross section going across here. Are my bounds going to change? No, so I'll keep those 0 to 4. Is the dy going to change? No, so I'll keep that. What about the formula here? Do I still use 1/2 pi r squared? No. What formula do I need if it's a square? Not x squared. How do you find the area of a square? Base times height, which is the same thing as side squared. All right, now watch this, guys. Do you see how this is representing the side on the square? Will you agree that that's touching not one xy ordered pair, but 2 xy ordered pairs on the parabola? So what is this side going to be? It's actually 2x. Which means this update is 0 to 4. If you square 2x, you're going to get 4x squared dy. Then from there, what did we say x squared was equal to? All right, so I got 4 still out there, and then 4 minus y dy is set up to that one.